There's a quiet assumption baked into modern computing that almost nobody questions anymore, that software is infinitely malleable. If a system breaks, we patch it. If it doesn't scale, we distribute it. If precision fails, we approximate and move on. From machine learning to global networks, we've built an entire technological civilization on the belief that clever engineering can always outmaneuver fundamental limits. But what if that belief is wrong? This conversation begins with a provocative idea, that there exists a structural boundary not imposed by hardware, not by energy, not even by complexity, but by mathematics itself. A boundary where our usual tools, floating point arithmetic, hashing, randomness, even neural architectures, quietly begin to fail. Not because they are poorly designed, but because they lack something deeper: rigidity. At the center of this idea lies a surprisingly ancient object: prime numbers. Long treated as abstract curiosities or building blocks of number theory, primes may represent something far more fundamental. They are the only known system that guarantees unique composition, perfect reversibility, structured irregularity, and stability at scale, all at once. In this episode, we explore a bold framework sometimes described as arithmetic rigidity, not as a final answer, but as a lens, a way of rethinking computation, not as an act of control, but as a process constrained by deeper mathematical laws. Because if there is a boundary to what can be built, then understanding it may be more important than anything we build next.
Today, we're looking at a paper that basically argues everything we know about building computers, like scaling software, writing algorithms, is fundamentally capped by a structural wall.
Yeah, a wall we didn't even build.
Right.
Yeah.
A wall that is literally baked into the very fabric of reality. So welcome to the deep dive on this Saturday, May 2nd, 2026. Grab your coffee, settle in, because we are unpacking a paper called Arithmetic Rigidity: The Structural Uniqueness of Prime Numbers.
And I just have to say, the premise here is absolutely wild.
It really is. It claims that prime numbers aren't just, abstract mathematical concepts that we force kids to memorize in school.
Right, like flashcards.
Yeah, exactly. The paper argues they are literally the only computational substrate in the universe capable of scaling infinitely without collapsing.
Which completely flips the script on how we view the primitives of mathematics. I mean, we're so used to this Silicon Valley mindset, right?
The idea that software is just infinitely malleable.
Exactly. Like, you need a data structure. Just invent a new one. You need to process more information. You throw, 10,000 more servers at it and invent a cleverer algorithm. We treat computation like it's a completely blank canvas.
Okay, let's unpack this, because humans, and especially engineers, we have this deeply ingrained natural instinct to try and hack the system.
Oh, absolutely. We love a good workaround.
Right. We always try to replace old, rigid structures with modern generalizations. We assume primes are just, old news, like something from the 18th century, and surely we can just use bit sets or neural embeddings or some slick new continuous architecture to build better artificial intelligence.
Or global networks. And, to be fair to human ingenuity, most of the time, replacing older structures works brilliantly.
I like that all the time.
The entire history of computer science is basically just a highlight reel of successful abstractions. We abstracted binary code into assembly, then assembly into languages like C or Python.
Right.
But the core argument of this paper is that when you push a complex system to the absolute limit, like when you try to build something that scales not just to thousands of nodes, but to trillions or functionally toward infinity, that human-made canvas just shatters.
Breaks.
Shatters entirely. We hit a mathematical boundary, and we don't hit it because our processors are too slow or we don't have enough RAM. We hit it because the structural constraints required for a perfect, infinitely scaling computational system are so intensely tight that only one known structure actually satisfies them.
And that structure is the prime numbers.
The prime numbers, and that is what the authors call the arithmetic rigidity class.
Okay, before we get into the really heavy math here, I want to ground this for you listening, because it sounds abstract, but it's not. Think about a massive real-world software failure.
Oh, the Patriot Missile example.
Yes, back in 1992 during the Gulf War. An American Patriot Missile battery completely failed to intercept an incoming Scud missile. 28 soldiers died. And the reason it failed wasn't like a mechanical jam.
Or a misfired rocket, yeah.
Yeah, right. It was a rounding error, literally a rounding error. The system's internal clock measured time in tenths of a second, but it stored that value using an inherently imprecise mathematical structure, a floating point number.
Which is how most computers handle decimals.
Exactly. And over 100 hours of continuous operation, that tiny decimal rounding error compounded. It drifted. And when it was finally time to calculate the exact location of the incoming missile, the system was off by more than half a mile.
That is just a phenomenal example of what happens when a computational substrate lacks structural rigidity. The local rules, those tiny fractions of a second, they failed to translate into a globally stable geometry.
They just fell apart.
The system drifted into fatal noise.
And that's just a single missile battery running for a few days.
Yeah.
Now imagine we're trying to build artificial intelligence models with hundreds of trillions of parameters, or trying to simulate the climate of the entire planet over a century. The stakes are astronomically higher.
They are. And the authors of this paper argue that to build systems of that magnitude, your foundational substrate must simultaneously satisfy 4 very specific engineering constraints.
4 impossible constraints.
Right. Historically, demanding all 4 of these at the same time has been considered practically impossible.
Let's break down these 4 impossible constraints, because I read that section of the paper like 3 times. And I want to make sure we really walk through the mechanics of this. It's the engine of the whole theory. So constraint number 1 is called multiplicative identity, or no aliasing.
Right. So in any complex system, you have basic building blocks. For constraint number 1 to be satisfied, every single component in your system needs to have a completely unique fingerprint.
Okay.
But it's more than just slapping an ID badge on a piece of data. That fingerprint has to survive being combined, multiplied, or layered with other components. If you combine component A and component B, the resulting state must be absolutely unique.
And distinct from, say, combining components C and D.
Exactly. If they aren't distinct, information dies.
Well, I want to push back on this a bit, just to play devil's advocate. Don't we already have this in computer science? Like, hashing algorithms give every file a unique string of text. A database assigns every user a unique integer ID.
We do have identity, yes, but we struggle immensely with multiplicative identity at scale. Think about what happens in a massive artificial neural network. You have billions of weights and biases interacting. As data passes through these layers, the math is constantly combining and recombining.
Right. It's multiplying matrices all the way down.
Yes. And if you don't have perfect multiplicative identity, you get what engineers call aliasing.
Okay, walk me through a micro-simulation of aliasing. Like, how does that actually happen in a neural net?
Sure. So imagine the network is trying to learn the difference between a picture of a cat and a picture of a dog. To the computer, these pictures are just, vast arrays of numbers. As the network processes the cat image, it multiplies these numbers together to form an internal representation, a specific state.
Okay, I'm following.
Now, it processes the dog image. Because human-engineered systems use finite precision or floating-point math, like your Patriot Missile example, there is a statistical probability that the distinct combination of numbers for the cat and the distinct combination for the dog might mathematically round out to the exact same internal state.
Oh, wow. They collide.
They collide.
The network literally can't tell them apart anymore because their combined mathematical signatures they ended up being identical.
The information literally dies right there. It gets completely overwritten by ambiguity. You cannot build a truth-preserving system if your building blocks occasionally pretend to be each other when they get mashed together.
Which is why primes are so uniquely suited here.
Exactly. By the fundamental theorem of arithmetic, every integer greater than 1 is either a prime itself or can be factorized into primes in exactly one way.
2 times 3 is 6.
And nothing else in the prime number system multiplied together gives you 6. It is an absolutely perfectly unique fingerprint that survives infinite combinations without ever aliasing.
Okay, I see the power of that. If you build your system out of primes, collisions aren't just rare, they are mathematically impossible.
It's impossible.
So let's look at constraint number 2. Hierarchical factorization, or moving from local to global.
Once you have these unique building blocks, you need them to compose into larger global structures. But the critical requirement here is reversibility.
Reversibility.
Yeah, you need to be able to look at the massive global structure and deconstruct it back into its microscopic pieces perfectly. You need a reversible engine.
Like the ultimate set of Lego blocks. You can build this massive, complex castle, but you can also dismantle it piece by piece, and no blocks are magically fused together. They aren't lost.
That analogy works perfectly for the physical mechanics, but let's apply it to computation. In computer science, this property is the absolute engine of compression and inference.
Right.
Think about compression. How do we take a massive gigabyte-sized video file and shrink it down to a few megabytes so you can, stream it on your phone?
Well, we find patterns. We look for repeated blocks of data and replace them with shorter symbols.
Exactly.
We rely on the fact that the massive global file can be factorized into smaller, localized rules.
Okay.
If the system lacks hierarchical factorization, you cannot compress it.
You just have a chaotic pile of data.
Yeah. Without a clear path from the local microstate to the global macrostate, an AI cannot infer the rules of the system just from looking at the raw data.
It's blind. So Constraint 1 gives us unique, indestructible parts, and Constraint 2 ensures those parts can build complex, reversible structures.
Which brings us to Constraint 3. And honestly, this is where the paper starts sounding a lot more like quantum physics than computer science.
It really does.
Non-lattice spectrum,
Yeah.
or no harmonic traps. Let me try to clarify what a spectrum means here, because when I hear spectrum, my brain immediately goes to a rainbow.
Okay.
But we're talking about frequencies of a system, correct?
Right. In the context of dynamical systems, a spectrum refers to the set of frequencies or energy levels at which the system naturally operates. If you think of a computer algorithm searching for a solution, it moves through different states. The timing and spacing of how it transitions between these states, that is its spectrum.
Let me bring in a physical analogy to visualize this because it helped me a lot. Imagine an army marching across a suspension bridge.
A classic physics problem.
Exactly. If every soldier marches in perfect, regular step, meaning their footfalls hit the bridge at a perfectly evenly spaced frequency that creates a lattice spectrum, it's this perfect grid of energy. And what happens? That regular spacing creates resonance.
The bridge starts to sway.
Yeah, the energy compounds with every perfectly timed step, and eventually the bridge can literally tear itself apart and collapse. So to cross safely, the commander orders the soldiers to break step. They walk with structured irregularity. They're still moving forward purposely, but they aren't locked into that deadly perfect rhythm.
That bridge analogy maps beautifully to mathematical optimization. If you build a computational system on a perfect, regular grid, what we call a lattice spectrum, it will inevitably hit a harmonic trap.
You get stuck.
Let's say you're training a massive AI and you're trying to find the absolute lowest point of error. The system acts like a marble rolling down a hill looking for the lowest valley.
That's gradient descent,
Yeah.
right?
But if your mathematical substrate is a regular lattice, the landscape the marble is rolling over is perfectly repetitive. It looks like an egg carton.
Oh, I see.
The marble will roll into one of those little cups, look around, and because the landscape is perfectly periodic, it thinks it has hit the bottom. It gets trapped in a local minimum. It just spins its wheels in that same periodic cycle forever, totally unable to break out and find the true global valley.
So a lattice spectrum basically guarantees your system will eventually get stuck. It becomes a victim of its own perfect symmetry.
To avoid this, your system needs exactly what those soldiers on the bridge needed: structured irregularity. The spacing between the components cannot be totally ordered, but it can't be pure random noise either.
Right.
And the prime numbers have this incredible property. The gaps between primes, the distance from 2 to 3, then to 5, then to 7, then 11, 13, there is no regular grid. The gaps vary.
These seem totally unpredictable locally.
But they follow a massive overarching distribution law globally. They inherently break the harmonic step.
Structured irregularity. It's like the system needs to constantly surprise itself just enough to keep moving forward, avoiding the traps, but not surprise itself so much that it loses its mind and falls into complete chaos.
Which is the perfect segue to the fourth and final constraint, asymptotic control, or stability at scale.
Hold on, let me stop you there. What does asymptotic actually mean for someone who hasn't taken a calculus class in 20 years?
Fair question. An asymptote is a line that a curve approaches as it heads toward infinity. When we talk about asymptotic control in computer science, we're asking a really simple question. What happens to the system when we scale it up to an infinitely large size?
Because, everything works fine when it's small on my laptop.
Exactly. Hand-tuning a small system to avoid errors is easy. You can build a toy neural network with 100 parameters and it will run perfectly. But asymptotic control means that as the system grows to billions, trillions, or practically infinite components, its macroscopic behavior must remain predictable.
The noise can't take over.
Right, the density of the information, the inevitable fluctuations, the noise they law must remain mathematically bounded. They cannot grow faster than the system itself.
So the system doesn't just drift off into useless static or suddenly explode into chaotic, unpredictable behavior just because you added a trillion more nodes.
If you're building a planetary scale data architecture, you cannot have a foundation that structurally degrades as it gets larger. It absolutely must hold its shape at infinity.
Okay, I really want to pause and review this impossible checklist. We need components that never lose their identity when mixed. We need them to form complex, perfectly reversible structures. We need their spacing to be perfectly irregular to avoid harmonic traps. And we need the whole thing to remain perfectly bounded and stable, even if we scale it up forever.
That's the list.
Are you telling me this is actually impossible for humans to build synthetically? Because we bit the internet. We sent probes outside the solar system. Surely a room full of brilliant software engineers can code a substrate that does all four of these things.
Human intuition runs headfirst into a mathematical reality here. This is a concept the paper refers to as the closure phenomenon.
The closure phenomenon. What exactly is closing?
The design space. When engineers build systems, they are used to making trade-offs. You want more speed. You sacrifice some memory. You want more security. You sacrifice some usability.
Standard engineering.
Right. The design space is vast, and you can explore different corners of it. But when you mathematically demand all four of these specific constraints simultaneously, the design space does not expand. It violently collapses.
It shrinks down to almost nothing.
It shrinks down to a very narrow, rigorous regime known as the Arithmetic Rigidity class. You cannot engineer a synthetic solution here because mathematical truth dictates that breaking even one of these constraints destroys the whole architecture.
Let's test that claim. I want to play devil's advocate for a minute. I know software engineers, and I know they have tried to beat this. Let's walk through the graveyard of obvious replacements.
Oh, the graveyard is full.
Let's systematically dismantle the alternatives humans have tried to use at industrial scale. Let's start with bit sets and hashes. We use these everywhere in modern computing. Every time you log into a secure website, a hashing algorithm is protecting your password. Why can't we build a massive AI substrate entirely out of bit sets?
Well, bit sets and hashes are fantastic for constraint number one. They give you perfect identity. You can take any piece of data, run it through a cryptographic hash function, and get a unique string of characters. But structurally, they are completely flat.
What do you mean by flat? My password hash isn't flat. It's just, a really long string of letters and numbers.
By flat, mathematicians mean there is no inherent geometry or hierarchy. Think about the numbers 3 and 6. Mathematically, 6 is built out of 3. There is a relationship there.
A factorization.
Exactly. Now think of a hash of the word cat and a hash of the word cats. The resulting strings are completely different. They have absolutely no relationship to each other. You cannot take a million hashes, multiply them together, and organically grow a structured, reversible global architecture. They don't compose hierarchically.
They just sit there, perfectly unique, perfectly isolated, and completely antisocial.
They cannot scale into a globally coherent structure. So, bit sets fail constraint number 2.
Okay, bit sets are out. What about floating point systems or irrational weights? We use floating point math for almost all modern physics simulations, video games, and AI training. An irrational number, like pi, goes on forever without repeating. It's infinitely complex. Why can't that be our substrate?
On paper, in pure Platonic mathematics, irrational numbers look like perfect candidates. They seem completely independent. But we don't run computations in Platonic heaven. We run them on physical hardware silicon chips with limited memory.
Right. A computer eventually has to stop calculating pi. It has to round off the decimal because it only has 64 bits of memory to store that specific number.
And the moment you round off a number, you introduce a tiny margin of error. You introduce noise. Let's go back to your Patriot Missile example. Or think about a self-driving car's AI trying to calculate the distance to a pedestrian. It uses a floating point number. Deep within the billion layers of its neural network, at 100th decimal place, it chops off the number.
It seems harmless. Who cares about the 100th decimal place?
At a small scale, nobody cares. But at a massive planetary scale, at an infinite asymptote, that finite precision causes the exactness of the system to collapse. Two slightly different irrational weights, when rounded, become the exact same number to the computer.
Aliasing again.
You lose the multiplicative identity. The exactness devolves into a noisy blur. Your system aliases.
So floating point math is out because physical reality forces it to lose its memory. It fails constraint 1 at scale.
Okay, moving through the graveyard. What about lattice spectra, regular grids? We talked about the bridge analogy and how they create harmonic traps, but we use regular grids because they are computationally cheap and incredibly easy for humans to understand. Pixel grids on a screen, voxel grids in a 3D simulation, spreadsheet matrices. They give us beautiful, easily digestible structure.
But the marble gets stuck in the egg carton.
The marble gets stuck. If you build a complex dynamical system like a predictive model for global economics on a lattice grid, the system will eventually find a resonance pattern. It will lock into a periodic cycle. It cannot explore new states because the geometry forces it to repeat itself. It fails constraint 3 entirely.
Okay, if regular grids are too orderly and trap the system, why not go the exact opposite route? Pseudorandom sequences. Just inject some controlled chaos into the system to break the resonance. Break the step of the soldiers.
Pseudorandomness definitely avoids the harmonic traps locally. It keeps the soldiers breaking step, but it completely lacks a global analytical skeleton. Pseudorandom numbers are generated by algorithms designed to look random, which means they intentionally defy hierarchical factorization.
Because if you could easily factor them back into a neat hierarchy, they wouldn't actually be random.
Exactly. And because they lack that structure, they cannot support asymptotic control. As you scale a pseudorandom system up, you cannot mathematically guarantee its stability. The fluctuations aren't bounded by a rigid geometry. Eventually, the simulated randomness will drift off into true, unrecoverable chaos.
Man, this is a brutal game of whack-a-mole for computer scientists. You fix the resonance problem with randomness, but you lose the stability. You fix the stability with a regular grid, but you get trapped in resonance. You fix the identity with hashes, but you lose the hierarchy.
It's rough.
We have one more alternative in the graveyard, though. Quasi-Crystals or aperiodic tilings.
Ah, yes. This is usually the last refuge of the desperate mathematical engineer.
I've seen pictures of Penrose tilings. They're these beautiful geometric patterns, usually made of diamonds and kite shapes that fit together perfectly and cover a floor, but the pattern never, ever repeats itself perfectly.
Quasi-crystals are brilliant. They achieve a stunning global order, and they have non-lattice spectra. Because the pattern never repeats exactly, they naturally break the harmonic step, avoiding the lattice traps, while still looking incredibly structured.
So what's the catch? I mean, they seem to solve the exact problems we just outlined.
They completely lack multiplicative factorization. There is no clean, reversible engine to go from local to global.
I'm struggling to visualize that. If I have the tiles on the floor, can't I just look at them and see the pattern?
You can look at the whole floor and appreciate the pattern visually. But imagine you are a computer algorithm. You are dropped onto a single tile in the middle of a massive quasi-crystal floor stretching to infinity. You look at your tile and the immediate tiles touching yours. In a system built on primes, you could perform a mathematical operation algebra on your local patch and instantly deduce the properties of the entire infinite floor.
Because the local factors perfectly into the global.
Right. But in a quasi-crystal, you cannot. You cannot organically grow the rest of the floor algebraically from a single tile. They have geometry, but they lack the underlying algebra that allows for computation, inference, and compression. What's fascinating here is how brutal and unforgiving this filter is. We just walked through 5 of the most powerful computational tools humanity has ever devised, tools that run the modern world. And in every single case, when you push them to the absolute limit and demand all 4 constraints, breaking just one constraint is totally fatal. The system fragments, it traps, it blurs, or it drifts.
The universe really does not negotiate. You cannot have 3 out of 4 constraints and call it a day. The system will fail.
Exactly. This proves why the arithmetic rigidity class is currently the only known survivor in this rigorous design space.
All right, so our synthetic systems shatter against the wall. We know primes are the only survivors. But how? What is the actual mechanical engine under the hood of prime numbers that allows them to pull this off so perfectly? How do they survive the whack-a-mole game?
To understand the mechanism, we have to look at the mathematical signature of this rigidity. It is an equation known as the Euler product formula.
Here's where it gets really interesting, because we are transitioning from primes are a neat mathematical curiosity to primes are the physical engine of reality. Walk me through the Euler product. Who was Euler, and what was he trying to do?
Leonhard Euler was a Swiss mathematician in the 18th century, arguably one of the greatest in history. He was playing around with infinite series-long lists of numbers added together. He formulated an equation that links two seemingly completely different mathematical worlds. On the left side of the equation, you have an infinite sum of integers. 1 plus a half, plus a third, plus a quarter, stretching to infinity.
That eventually became known as the Riemann Zeta function, right?
Later on, yes, when Bernhard Riemann extended it to complex numbers. But Euler's genius was showing that this infinite sum of continuous, smooth fractions is exactly mathematically equal to an infinite product involving only prime numbers.
Wait, let's pause there. An infinite sum of fractions equals an infinite product of primes. Why is that such a big deal structurally?
Because on its face, it looks like just a neat algebraic trick. But structurally, what this paper argues is that the Euler product is the only known mathematical mechanism that simultaneously encodes all four of our impossible constraints into a single object.
I am still struggling to see how one 18th century formula does all the heavy lifting for a massive AI scaling problem. Explain to me step by step how an infinite sum and an infinite product prevent a system from collapsing.
Think of it as the ultimate interface. On one side, you have the primes. They are discrete. They're individual building blocks. Because they are primes, they guarantee constraint number one, multiplicative identity. They never alias.
Okay.
On the other side, you have the global sum. Because Euler proved you can move back and forth between the local primes and the global sum with absolute mathematical equivalence, he proved constraint number two, hierarchical factorization. The local algebra perfectly composes into the global geometry reversibly.
Let me expand on an analogy here, because thinking about it as an interface helps tremendously. Think of the Euler product as the most perfectly coded software API in existence.
Oh, I like that.
Yeah, an application programming interface is how different pieces of software talk to each other. When you buy something on an app, an API connects your discrete click to a massive, continuous global banking network. Now imagine an API that flawlessly translates billions of tiny, discrete, individual user actions, that's our local algebra, our prime numbers, into a massive, smoothly running, globally coherent software ecosystem.
The global geometry.
Right, and it does this without a single microsecond of lag, without ever crashing, and without losing a single piece of user data. It translates the discrete into the continuous seamlessly.
That is precisely the mechanical function of the Euler product. It is the bridge. And when you build a dynamical system on top of this specific interface, you discover a physical property called entropy rigidity.
Entropy rigidity. Okay, we need to define that carefully without falling back on sci-fi tropes. How does entropy rigidity actually behave in a physical or computational system?
Let's use a mechanical metaphor. Imagine you have a large sheet of glass. The glass represents a smooth, continuous mathematical space, what mathematicians call a smooth manifold. If you apply a massive amount of pressure to the center of the glass, what happens?
It bends slightly and then it shatters entirely. The local stress just destroys the global structure.
Right. Now imagine, instead of a sheet of glass, your system is built out of a tightly woven fabric made of Kevlar, but the weave is specifically structured according to the prime numbers. When you apply immense pressure to that fabric, the unique interceptions, the primes, allow the fabric to distribute the stress across the entire global structure without tearing.
It holds together.
The spectrum of the system is so incredibly compressed and resistant to deformation that changing the local parameters barely alters the global behavior. The system fiercely protects its own structure. It absorbs the entropy.
It doesn't shatter. It distributes the load perfectly across the irregular but structured web.
And recent work in spectral geometry has shown that this specific type of rigidity, this stress distribution, is entirely absent in smooth manifolds or random graphs or any of those lattice systems we talked about earlier.
Let's define smooth manifold and random graph quickly, because my brain hears manifold and goes straight to car engines.
Fair point. In mathematics, a smooth manifold is basically a space that, if you zoom in close enough, looks flat and regular, like the surface of a sphere. A random graph is just a collection of nodes connected by entirely random links. Both of those structures fail to distribute stress at an infinite scale. The smooth manifold bends and breaks, the random graph drifts into chaos. The entropy rigidity only appears when the underlying substrate carries the multiplicative independence of the primes.
So the prime numbers aren't just getting lucky. They aren't just a neat pattern on a number line we happen to notice. They are actively enforcing the structural stability of the system. They are the Kevlar weave.
They are enforcing it. The primes are the only known substrate that can maintain that Kevlar weave at an infinite scale without a single flaw, which forces us to look at them not as abstract numerical concepts, but as a deeply physical, deeply geometric reality.
If this Euler product API is perfectly translating the local prime numbers into a massive global geometry, where is the output? What does that generated geometry actually look like?
That is where we cross into what is arguably the deepest, most beautiful concept in all of mathematics. Duality, two sides of the same coin. The output of that geometry is found in the non-trivial zeros of the Riemann Zeta function.
The famous Riemann hypothesis zeros, the million-dollar math puzzle that has stumped people for a century.
The very same. But this paper frames their relationship in a way that is absolutely vital for understanding computation. Through the Euler product, the primes and the zeros are bound together in a dual relationship.
Explain duality to me in this context. How can a prime number be dual to a zero on a graph?
The primes are discrete. They are multiplicative. They are structural. They are the atoms of the system. The zeros, on the other hand, are continuous. They are spectral. They are dynamical. They are the frequencies of the system. They represent the macroscopic wave behavior of the space generated by the primes.
I want to make sure I'm visualizing this clearly. Compare the primes and the zeros to music. The prime numbers are the discrete individual notes written down on a piece of sheet music for C sharp and E at G. They are structural, distinct, and they sit isolated on the page. You can literally point to them.
Yes.
The zeros of the zeta function are the continuous sound waves traveling through the air when an orchestra actually plays that sheet music. They flow, they interact, they're a continuous dynamic frequency. The sheet music and the sound waves look completely different, they behave differently, but they are two completely different languages describing the exact same underlying song.
If we connect this to the bigger picture, your music analogy captures it perfectly. In mathematics, they are linked by things called explicit trace formulas.
Trace formulas.
Think of a trace formula as the physical dictionary that translates the particles into the waves. It proves that the discrete sum over the primes is mathematically identical to the spectral sum over the zeros. Moving from the primes to the zeros isn't changing the system. You are just rotating the coordinate system. You're looking at the exact same rigid structure through a different lens. One lens shows you the particles, the sheet music. The other lens shows you the waves, the sound.
And this totally recontextualizes the Riemann hypothesis for me. For decades, the Riemann hypothesis has been talked about as this highly abstract puzzle. Where do the zeros lie on a complex plane? Let's prove they all sit on this one specific vertical line called the critical line. But in the context of arithmetic rigidity, it's not just a geometry puzzle, is it?
Not at all. The Riemann hypothesis in this framework is a literal claim about the asymptotic control of the entire computational system of the universe.
Hold on. Walk me through that. How does a zero sitting on a line equal asymptotic control?
The Riemann hypothesis posits that all the non-trivial zeros lie on a line exactly at x equals 12 on the complex plane.
Why 12 specifically?
The number 12 mathematically represents a square root bound. In statistics, if you have a random walk, a drunk person stumbling around taking random steps, the distance they wander from their starting point grows proportionally to the square root of the number of steps they take. It's bounded. If the zeros sit exactly on that 12 line, it means the fluctuations, the noise generated by the primes as they scale to infinity are perfectly bounded by that square root limit.
They're contained.
They are contained. It means the system scales perfectly. The sound waves from your analogy don't suddenly spiral into deafening, chaotic noise as the music gets infinitely loud. But if the Riemann hypothesis is false, if even a single zero drifts off that critical line of 12, the scaling stability collapses. The bounded fluctuations explode. The universe's ultimate algorithmic structure would have a fatal bug.
So proving the Riemann hypothesis isn't just about a mathematician winning $1 million from the Clay Mathematics Institute. It's about proving that the foundational computing substrate of reality is fundamentally stable at infinity. It guarantees that the primes can do their job forever without the system tearing itself apart.
It guarantees the architectural integrity of the mathematics governing reality.
We have covered some incredibly deep mathematical and geometric territory here. We understand the constraints, the catastrophic failures of human engineering, the Euler API, the Kevlar weave, and the music of primes and zeros. But I want to pull us back down to earth. So what does this all mean for you listening right now, sitting at home, or for the computer scientist who is trying to debug a massive, complex network? How does this actually change our reality today?
It initiates a total paradigm shift in how we approach computation itself. Traditional computer science is built on a very specific mental model. We treat hard computational problems as discrete combinatorial searches.
Finding a needle in a haystack. You check every piece of hay until you find the needle. And if the haystack is too big, you write a cleverer, faster sorting algorithm to check the hay.
That has been the dominant framework for 70 years. But arithmetic rigidity suggests a completely different framing. It suggests we should view computation not as a search algorithm, but as a constrained physical evolution on a structured manifold.
Let's translate that out of jargon. What does constrained physical evolution actually mean for a server farm trying to optimize, say, a global supply chain?
It means we stop thinking about solving a problem as executing a series of logical if-then steps. Instead, we start thinking about it like physics. Imagine dropping a marble into an incredibly complex, multidimensional bowl and watching how gravity pulls it down to the absolute lowest point.
Energy minimization. The system naturally seeks a state of rest.
Energy minimization. Under this new framing, a hard computing problem isn't just a problem that takes a long time to compute because the algorithm is slow. Hardness is a physical phase transition. The system literally freezes up like water turning to ice. Solving becomes the act of energy minimization under rigid constraints. And tractability, whether a problem can practically be solved at all by a machine, is determined entirely by the geometric structure of the substrate, not by how clever your Python code is.
So if you were designing a massive artificial intelligence model today, or trying to optimize the logistics network for global shipping, all the algorithmic cleverness, all the slick coding, all the processing power in the world is not going to save you if the underlying substrate you are building on lacks arithmetic rigidity.
That is the hard truth this paper exposes. If your foundational structure relies on floating point approximations or flat bit sets or pseudo-randomness, the geometry of your problem will eventually betray you at scale. The system will fragment due to aliasing, or it will get trapped in local minimaker. Your marble gets stuck in a tiny divot in the egg carton and never reaches the bottom of the bowl. But systems that possess arithmetic rigidity remain coherent. They scale predictably because their constraints are anchored in a structure that is exact, hierarchical, and analytically bounded.
It's a massive reality check for the tech industry. We aren't the omnipotent gods of the digital universe, shaping clay however we want. We are just tenants living in a rigid house built by prime numbers.
I wouldn't call primes magic, though. We don't need to mystify them. It is simply an empirical and mathematical observation. When you force algebra, geometry, dynamics, and computation to sit down at a table together and perfectly agree on the rules for scaling, the primes are the only structure we currently know of that satisfies all parties without contradiction.
Which brings us to the ultimate synthesis of our deep dives today. We have explored how identity, hierarchy, irregularity, and stability converge into a razor-sharp boundary.
And the prime numbers, along with their spectral duals, the zeros, are the canonical and currently only known realization of that exact convergence. It is the precise intersection where truth-preserving computation meets the fundamental number system itself.
The scientific landscape has dramatically shifted because of this perspective. A decade ago, a mathematician or a computer scientist might have asked, why should we use primes for this system? Let's just invent a better hash. But today, the burden of proof has entirely flipped.
Absolutely. The scientific community isn't asking why primes anymore. The challenge thrown down to every computer scientist, physicist, and mathematician is now. What else survives? What other structure can you possibly build that survives all four constraints at an industrial infinite scale?
We've tested the bit sets, we've tested the continuous floating points, we've tried the quasi-crystals. They all fail when you push them to the limit. Until some can produce a mathematical counterexample, until a brilliant engineer can build a new substrate from scratch that satisfies the closure phenomenon. The edge of efficient computation is inherently arithmetic. It belongs to the primes.
This raises an important question, perhaps the most profound question we can ask based on this material. We've established that primes are the absolute boundary class for stable, scalable, truth-preserving systems. We know they act as the ultimate interface between the discrete particles and the continuous waves.
The sheet music and the sound.
Right. If we look at the physical universe around us, what is the single greatest unsolved mystery in physics today? It is the intersection of discrete quantum mechanics, the behavior of subatomic particles, and continuous general relativity, the smooth fabric of space-time and gravity. They refuse to play nicely together in our equations. Yet the actual universe somehow perfectly balances discrete quantum particles with continuous wave functions without collapsing. It scales infinitely from microscopic quarks to massive galaxy clusters while maintaining perfect asymptotic control.
Oh, wow. I see the parallel you're drawing.
Could the fundamental laws of physics themselves be running on an inherently arithmetic substrate? Are prime numbers not just the foundation of abstract math, but the actual literal source code of physical reality? Is the universe computationally stable precisely because it is built on the arithmetic rigidity of primes?
That is a thought that will keep you awake at night. We started this hour by imagining you were an architect, frustrated that you couldn't build a digital skyscraper out of whatever synthetic material you wanted. We realized the mathematical X-ray machine wasn't broken. It was just showing us a skeletal structure we didn't invent, but that we absolutely depend on to survive. Prime numbers aren't just something to be memorized. They are the load-bearing pillars of reality.
A structural necessity for existence.
Thank you so much for joining us on this deep dive. Keep questioning the structures around you, because as we've seen today, the most profound secrets aren't always hiding out there in the stars. Sometimes they are hiding right inside the numbers we've known since childhood. Until next time.